On to part whatever this is of integration. And again, if you haven't seen the parts leading up to this, you're going to be really confused. We have a cylinder now. And as you can see, we're going to be slicing the cylinder up just like slicing cake layers, right? And so let's start with, you know what, let's find surface charge, total charge via surface charge density this time. So let's say that we're told that the surface charge density of this cylinder varies like this. In other words, it's a constant plus some other constant that changes along the z-axis. So there's very little charge down here, just A, right? But as we move up along this cylinder, we're going to get more and more charge as we get to the top. And again, we want to find the total. So we're going to fall back on our method. Our total is going to be found by adding up little tiny pieces of charge. Since our charge density is a surface charge density, we're going to take advantage of that. We know that sigma is equal to the total charge divided by a surface area, which means that our dq is going to be sigma dA. And now we get to the question, the hard question in all of these integral setups. What am I going to pick for this differential area? As you can see over in our diagram, we're going to take advantage of the fact that it's changing in the z direction. We want to use all other directions. We want to use the radius of this cylinder. We want to use the fact that it kind of goes around, that all of that stays the same. So we're going to take advantage of that by taking a circle, basically, right, all the way around, and then we're going to find a surface area by bumping up in the direction of z. So this is going to be like a thin strip, right? Like a ribbon that kind of goes all the way around, and it's the surface area of this ribbon that goes around that we are going to take advantage of finding. I apologize for my horrible, horrible drawings. You know what? We should get rid of that one because that's just terrible. All right, so we're not finding a volume of that disk, we're finding the outer surface area strip of it. Okay, so that means I need, so this area, it needs to have units of area, which means it needs to have distance squared in it. How am I going to find the area of that strip? Well, I'm going to take the circumference of a circle, 2 pi r, right? And then I'm going to multiply by a change in length or change in z of my cylinder. Check the units, right? Units here are r and z, so that's meters and meters. So good, I've got meters squared. So that means I've got an area, but does the area make sense? Is it an actual area? Well, the answer is yes. I take a line all the way around, and then I kind of bump that line up. I'm going to get a surface area. So away we go. We can go ahead and stick this up into here. It's going to be the integral of sigma 2 pi r dz. We're going to go from 0 to whatever the length of my cylinder is. I'll just, I don't know, just 0 to L. And then pull out some constants. Now I'm doing math, right? 2 pi r dz from 0 to, oops. You know what? Back up. Doing math wrong. Turned my brain off. Sigma, right? The 2, the pi, and the r all come out. Those are constants, right? They're not changing in this integral, but sigma does, right? It's a plus bz, and then dz from 0 to L, 2 pi r az plus bz squared over 2, evaluated from 0 to L. So it's going to be 2 pi r AL plus BL squared over 2 minus, and then 0 plus 0, right? Let me stick in the 0 limits there. And what am I left with? 2 pi r AL plus BL squared over 2. And that will be in coulombs. There's the total charge on that cylinder. For completeness, I want to do this again but use a different method of cutting up the sphere, so to speak. Let's say we're given a surface charge density that goes as A cosine theta. So this is kind of doing something strange, right? The charge density around this cylinder is wiggling kind of up and down in its intensity. There's areas, there's parts of the outer edge of this cylinder that have zero charge, and then there's other places that have lots of charge. So it's varying all the way around. And again, we want to find the total charge on this cylinder. Well, again, we're going to find that by breaking it up into little parts of Q. That's going to be sigma dA. But now the question is, what do we do with this area? Again, we want to be clever. We want to think of this area. How can we write this down so that only one thing is changing? Well, the answer is lying right over here. Really, it's only this angle that's changing, right? And so we're going to take advantage of arc length to be able to do this. Again, I need an area, but what we're going to do is we're going to cut this cylinder up into pie slices or cake slices. So when we cut a cake, normally when people cut a cake, right, and they're cutting a slice out of cake for themselves, comes out wedge shaped, right? Comes out kind of shaped like this. That's much better than my ribbon, okay? And so what we need to do is we need to find the surface area of this piece right here, okay? Well, I'm gonna find that surface area, right, by figuring out, right, what this dimension is and then multiplying it by this dimension. So I already know what the top dimension is, the length of the cylinder, right? But it's this dimension that is going to be variable, and it changes with the angle. So what is the total surface area of this part, right? Well, it's going to be the length, right, the vertical part, times the arc length, right? And arc length is r theta, but here it's going to be r d theta, right? Because we're not doing the total theta around, we're just doing the little d theta part right there. So this is arc length, right? And this is just the height. We put those two things together, we get an area, we have units of area, and we are good to go. It's going to be integral of LR d theta from 0 to 2 pi, since we want to go all the way around the, sigma LR d theta going all the way around. So performing the integral, I will try to keep my brain locked in here. This is going to be LR integral 0 to 2 pi of sigma a cosine theta d theta. Again, the L and the R come out because they're not changing in the integral. They're staying the same, right? And then I can pull the A out because it's not changing. I have the integral of cosine of, oops, that is not a cosine. Not even by Mr. Balogh handwriting standards. 0 to 2 pi cosine theta d theta, and the integral of cosine theta d theta is sine theta, evaluated from 0 to 2 pi, and when we do that, we get 0. Wait a second, Mr. Balogh, what the heck happened? Well, we integrated around cosine theta completely. And if you go around a full period of 2 pi of any cosine or sine function, you're always going to add up to 0, right? The function stays above just as much as it stays below the axis. And so it should come as no surprise that this charge varies as positive q, then goes to 0, then goes back to negative q, and then back up to 0, and so on and so forth all the way around, that when we finally add all of this together, we're going to get 0. Again, not the result that we want to focus on, but this process, right, of figuring out what that differential needs to be. This is the part that you are going to struggle with, that everybody struggles with in Physics 4B. And so being exposed to this and practicing it and doing it are going to keep you, it's going to give you a leg up in the chapters to come.